Hello, hello. Good morning, good afternoon, good evening, everyone joining us all around the world. Welcome to another SNIA educational presentation delivered via BrightTalk. And we are presenting the data reduction series today. In particular, we are going to go deeper into the compression and storage, which has been an increasing part of our discussions. Let me introduce myself first. My name is Ilker Sibeli. I'm going to be your host and moderator for today's webinar. I am a senior director at Samsung in storage product planning. I'm going to be fielding your questions and providing the basic administrator for this webinar. But first, I need to introduce you a few key points concerning the BrightTalk interface, especially those of you who may not attended in the past previously. First, you can expand the screen size. This may be important if there are any details during the presentation that may appear difficult to read. Simply click on enlarge the screen, the full screen mode. The second of all, you can ask questions during the presentations by selecting the ask question option, entering your question. We will have time at the end of the presentation. However, I may field some of the questions during the presentation. The third, and importantly, please rate the presentation. This is important to us. It gives us the solid indication whether we are delivering the right quality of content. So please rate the presentation at the end. A score of 1 means you would rather have spent the time more wisely. Score of 5 means it's perfect for you. You want to come back again. And also, you can download the attachment of this presentation. There's an attachment link. You may also send us comments and feedback on our webcast program and let us know if we are covering the topics you would like to hear. So please allow me to introduce today's distinguished speakers, Brian Will and John Kim. John is a director of marketing at NVIDIA, also chair of the SNIA Networking Storage Forum. Brian is a senior software architect in Network Platforms Group at Intel, focused on lossless compression and TLS and SSL protocol for Intel Quick Assist technology. So John, Brian, gentlemen, please say hello to the audience and a few words, please.
Hello, Ilker. Hello, everybody. Great to be here. Looking forward to this webcast.
Hello. It's great to be able to have this discussion on compression and its applicability to the storage.
Excellent, excellent. Okay, let's talk about some of the SNIA initiatives. So if you're not familiar with SNIA, let me give you a quick overview. SNIA is a global nonprofit association dedicated to advancing the adoption of storage technologies. We do so by using our vendor-neutral status, and we work to develop industry-wide standards. And to do that, we enlist the help of the subject matter experts in our membership community, such as John and Brian. And we provide some of the marketing and promotional programs to help in that adoption. But as I said, we cover all things storage, and this is just some of the things that we've been working on, but we have a large number of current projects that we haven't quite made the list yet. SNIA also provides an extensive range of educational materials on storage technology to help the industry and storage user community to better understand the implementation and deployment challenges. Our educational materials take many forms, including webcasts like this, and you will see presence at many industry events, giving talks on the technology subjects. So just before we get into details of the presentation, this is a standard legal disclaimer I have to present from SNIA. The basis of this is to remind you that the material is SNIA copyright and the conditions under which the material may be used. Second of all, state that SNIA is not providing any legal advice here and is also not providing any warranties expressed or implied in the content of this presentation. And please use of the material at your own risk. So for today's agenda, we will first section, John will be talking about compression, why, where, and what, how the compression relevant to different types of data. And Brian will take over the next section. It will talk about more technical areas on the data compression techniques and benefits. So without no further delay, please allow me to hand over to John today. John, please take over.
Ilker, thank you very much. Hello, everyone. This is John Kim, and I'm going to focus on why, where, and what to compress when it comes to data compression. And then Brian will take over and talk about compression technology and how it can be implemented. So first, why, where, and what to compress? Why would we do this? Where would we do it? And what is suitable for compression? So first, why compress data? So on the pro argument, why should I compress? Of course, it will save space. Of course, unless the files are already compressed. It can reduce the use of network bandwidth. So compression can reduce how much bandwidth you use, and in fact, in some cases, makes network transmission of data across the network faster, because the time saved from transmitting less data is greater than the time required to compress or decompress the data. Also, data compression used in storage is usually lossless. It usually does not lose any data. Though there are, as Brian will talk about, there are other methods that do lose data and are used in certain cases. Okay, but on the other hand, why might I not want to compress? Well, first of all, it does increase the amount of time to both write and read files. Compression takes time. It may not be a lot of time in some cases, but it does take at least some time. Second, it requires some processing power. So if you have a very busy server or a very busy workstation, compression can consume some of the valuable CPU cores that you are using. On the other hand, not all compression algorithms are processor intensive. Brian will talk more about this. So it's quite possible that your server or your workstation have enough extra CPU cycles that they can do regular compression and decompression without you noticing any impact on the performance of other applications. And finally, this is rare, but compression could pose a risk to long-term accessibility. If you compress with an unusual algorithm, or you somehow lose access to the algorithm or the software that's used to decompress that content, then 3 or 5 or 10 years from now, it's possible you'll go to read that content and you won't know how to decompress it. Of course, this is less likely if you use a well-known compression method, which has popular or open source libraries available to do the compression and decompression. Okay, where can we compress the data? Well, one place you can do it is in the application itself. A common use case would be applications that store photos or record video, or in fact, many cameras themselves will compress the data. So by the time it gets to the computer or the local drive or the network storage, it's already compressed. Also, applications, for example, browsers and web servers can often compress HTTPS information so that it loads web pages faster, because they save more time. The amount of time used to compress is significantly less than the time savings from transmitting compressed web pages. Another place you could compress is at the client in the operating system or in the file system. At the client using an application. For example, if you use a zip application, there are many out there, then you could go in and tell the application compress a certain set of files or decompress a certain set of files. Also, some operating systems or file systems do this automatically, both for workstations and servers. So in some operating systems, you can go in and just say, compress my drive, and it will go through and try to compress everything on your drive. A third place to do compression is on the network. So a WAN optimization appliance or a SD-WAN appliance may compress data as a matter of course, just to reduce how much bandwidth is required to transmit the data over long distances on the WAN. So this is actually quite common now with WAN controllers or SD-WAN optimization, or SD-WAN controllers or WAN optimization appliances, finally, the storage, of course, can compress it, where it's actually done by the storage controller or by the storage device. So now I think we're starting to see some computational storage devices that can compress the data so that the storage controller doesn't have to do it. You can do it during backup, of course, and this is also common. So the backup software or the backup hardware, whether it's on-premises or it's a cloud service, might compress the data to reduce space. In some cases, you can compress in more than one place, but this only usually makes sense if the data is being decompressed when it's retrieved or transmitted. because as we'll hear more from Brian, if the data is already being compressed, trying to compress it again usually is a waste of time and usually doesn't save any additional space. Just illustrating my slide, where can I compress the data? We see here that I could do it in the client app, which would be, for example, a browser or an application like Photoshop or a camera can compress the data. The operating system or utility can compress it. So again, many file systems and operating systems give you that option, and there are utilities that will compress the data. Once you get to the server, the same thing could happen. So for example, the database server might decide to do compression on the database tables, or the server operating system could compress. A storage can compress. Again, it's usually today done by the storage controller, but it's quite possible that in the near future, or even now, you might be able to compress in the storage devices. On the network, if I transmit a long distance, let's say from a remote office to the data center or from a data center to a cloud backup service, the networking equipment might compress the data and then decompress it when it reaches the other side. And as I mentioned, the backup server, backup device, or backup service might compress or deduplicate the data or do both. So compression is normally done in software. So now there are some CPUs that have optimized libraries to accelerate tasks like compression. And there are also, and there's usually optimized software APIs to access those CPU libraries. You can have special cards. You could have a FPGA card or a SmartNIC or a DPU. And these can be plugged into the server or the workstation to help accelerate compression so that they do it on the card instead of on the CPU. All right, moving forward, and let's have, I think the last part of the second last area is what should I compress? And basically, compression works best if a file has, or if the data has a lot of empty space, or if it has a lot of repetitive sequences which are local, meaning they're fairly close together, or those repetitive sequences are found in the same block, within the same file, or at least within the same drive or close together in the same storage device. Where you probably don't want to compress would be, of course, if the data is already compressed, because as I mentioned, that usually just wastes time, and in fact, compressing twice can take up more space, or if there's repetition, but the repetition is not local. So if you have a bunch of identical files, but the content within each file doesn't have a lot of repetition, then deduplication might be more efficient than compression, and compression may not work very well in that way. If you have dispersed block repetition, so I have a lot of identical blocks of data, but they're spread across different drives or different files, or otherwise far apart and not easy to access together, again, that makes compression not impossible, but difficult and inefficient to the point that it may not be worth it. And again, that could be a case where deduplication might make more sense than compression. So I think this is my last slide. So let me give an example. On the left, we have a file which should be very easy to compress. Why? Because first, it's all text. It has a lot of empty space where it's blank characters or filled with zeros. It's very easy to compress when you have many repetitions of the same character, even if the character is an empty space. And then the repeated sequences of letters, where A, B, C, D, or 5, 6, 7, 8, or my dog has fleas, these sequences appear over and over within one file. So Brian will talk more about what kind of span or how far compression technology can look for repeated sequences. But the fact that they're repeated sequences close to each other in one file usually makes this kind of file very easy to compress. On the other hand, we see a series of 9 files where there are repeated sequences. The exact same text appears, but it's not repeated within the same file. It's repeated across different files. So in that case, and there's not a lot of empty space or repeated letters inside each file. So in this case, file level compression is not going to work. However, compression could work if it's able to look across multiple files to find those repeated sequences. Again, Brian will cover that in more detail. But the second case on the right with those 9 files, that might be a really good candidate for deduplication instead of compression, and SNIA is planning a separate webcast that will do a deep dive on deduplication. All right, that done. Let me turn it back over to Ilker to see if there are any questions or anything, and then we'll go on to Brian to learn more about data compression techniques.
Hey, thanks, John. That was good. Actually, I just want to remind the audience, you can ask questions during the presentation by selecting the Ask Question option and typing your question. And I had a question for you on the dedupe. Actually, you did touch base. How would either John or Brian, you can what will be the difference? How is the compression different than deduplication? Either of you?
Yeah, let me give an answer, and then Brian might also want to add on to the answer or give his answer. So compression is actually kind of like a very localized dedupe, but and Brian's going to get more into this as he explains how the compression technologies work. But compression tends to look for repeated character sequences that are locally or fairly close together. Dedupe tends to look for identical blocks of data that are usually at a block level that are repeated, and they can be repeated more widely, meaning perhaps anywhere on the drive or even anywhere on the storage control on the set of drives in the storage, or possibly even across multiple storage devices or different storage controllers. Dedupe is able to find those sequences and represent them once instead of, so I find 10 repeated files, or the same file 10 times, I can save one copy of that file and just reference it 10 times. So dedupe and compression actually work in kind of similar ways, but dedupe tends to work at a block level on a much wider scope, and compression tends to work on a character or block level in a much smaller scope. Brian, perhaps you can give a better technical answer to that question.
Oh, that's a really good description of it. Exactly. The key to it is the locality of what you're searching for and the spans in which you search over. So when we get into the compression piece, we'll talk about history windows and the window that you look over. But dedupe is really looking for repeated blocks across many different areas or devices or even different systems. Whereas compression is really looking at an individual block of data, whatever size that might be, over a particular history window or stream of bytes, and it's much more localized.
Very good, guys. Actually, there's a related question from the audience. What is the difference between the compression versus a compaction? Do you get either of you guys want to take a stab at this?
Brian, do you want to do that, or I can, because we actually covered that in a recent SNIA webcast. Okay,
I'll let you take it, John.
Okay, so we actually just described compression, but compaction is, if I understand it correctly, is you go in and you find empty space and you scoot up the data to use the empty space instead of leaving a lot of empty space around. So for example, you might have a lot of data blocks which are only 20 to 50% full, meaning that half of each block or 70% of each block or 80% of each block is unused. Or you could have a file which has a lot of empty blocks which are just taking up space. So compaction means that you scoot all the real data up close to each other or adjacent to each other, and then you're able to take that unused space and either free it back up to the operating system or make it available for other files. Brian, do you want to expand on that?
Yeah, and generally my understanding of compaction is exactly that you're trying to remove unused area and trying to, say, reclaim possible alignment areas or issues that might have occurred during the writes or reads. Whereas compression is really looking at the byte stream and trying to remove repetition in the data and represent it in a more compact method.
Very good. Very good. Before we jump into one more, John, you did mention on your presentation what is DPU. Can you elaborate what is DPU to the audience?
Oh, sorry, I should have explained that acronym. So DPU means Data Processing Unit, and it's usually a smart type of network interface that can also process data and is programmable. And it's a fairly new term, but it's available from several vendors today. This isn't a good place to go into the details, but basically it's something which combines network interface with programmable processing to manage data as it goes in and out.
Very good. Okay, there are a few other questions, but I will leave them to the end, and then we'll try to answer them at the end of our Q&A session. Brian, you want to take over?
Okay. Yeah, thank you, Ilker and John. So what I'm going to cover is data compression techniques. So as a baseline, let's just identify what data compression is from a definition standpoint. So it's the process of encoding data to reduce its size. Now, at a high level, there are really two ways of compressing data, and that's the terms that tend to get used are lossless or lossy compression. Lossless compression, and you see the definition here, but it's essentially the process of compressing the data so that you have you can fully decompress it back to the original data set. There is no loss in the information during the compression process. Lossy compression is a technique that does lose data during the compression process and typically gets applied to applications that can handle that loss. So good examples would be image compression, video compression, and audio compression. Those are areas where you can, the human ear, visibility, can all handle loss in the data. Whereas if you're looking at raw data files stored on a file system that aren't identified as a particular data type or database information, all of those things really can't handle loss because you need full fidelity of the information when you decompress it. So those are the two categories that kind of live within the space of compression or in data compression. And what I'm going to cover here is really the lossless compression algorithms and that space of technologies. So if we look at lossless compression, there are a large number of them, different algorithms, and I'll cover some of them in the next slide. But a lot of them based down onto a few techniques. Usually you'll have a 1 or a 2 stage process, and those 2 stages are usually an LZ77 stage. This is where you're trying to reduce repetition in the data set by looking back in history within this window that I kind of mentioned before, and seeing if there's repetition that you can express in a smaller format. The encoding stage is really the idea of if you have an alphabet, is there a better way of representing that alphabet in a more compact manner? So I'll go through these 2 examples. So if you take the dictionary coding example or the LZ77 example, and you've got this tic-tac-toe repeating set of 3 letters, you identify 2 things. One is a min-match. So what is the most profitable match you can find, or the minimum most profitable match you can find? In this case, we're going to say 3 bytes is a good match because our encoding is going to go down to 2. It's going to be a distance and a length. So 3 is a good min-match to start with. And then you say within a window, what can I go look at? So I want to look back, and in this case, we're saying the window can be anything greater than 6 bytes. Possibly, and we go and look at the data and we say within that window space, what can we find? So let's take the first example. We find the first 9 bytes that come through are tic-tac-toe. We don't have any repetition of 3-byte sequences, and then we hit this tick. And what we do is we go back and we say, well, have we seen that before? And yes, we have. And then how many more bytes into the data stream have I also seen? So we see tick, we see tack, and we can replace that with a distance, so 9 bytes back, and a length. We're replacing 6 bytes. So essentially what this is telling it, go back 9 bytes and copy 6 bytes ahead, and that's your compressed data. And then we see the same thing when we hit the tack portion of that it can go back 3 bytes and then it can copy forward 3 bytes. So that's really the base concepts of LZ77. Now there's a lot of schemes and there's a lot of optimizations that can be put in that to get better compression. As you can imagine, you could find multiple matches back in history, and your algorithm has to decide which is the most profitable match to put down, and it has to decide that in the context of not only if it's a longer match replacement, but also in the context of how far back in history is it, and how many bytes is it going to take to encode those symbols of distance and length. So the algorithms can get quite complex in this space. Then a lot of techniques will also employ what's called an encoding stage. Good examples of these would be Huffman and arithmetic encoding. What I have here is a very simple just frequency coding. It's not a full Huffman tree. It's really just for example purposes. But the concept here is that if you take, say, an alphabet, say take the ASCII character set, in a real set of data, you're probably not going to encounter every single symbol in the ASCII character set. And even if you did, you're not going to get an absolute equal distribution of all symbols. So the frequencies of certain symbols are going to be much higher than other symbols. And because of that, it means you can create an encoding format that replaces those very high frequency symbols with smaller encoding schemes that then save you further space from a compression standpoint. So take, for example, T is the most repetitive piece in this data sequence. So we put that as the highest frequency, and it will get the shortest code, in this case, 0, 0. The next most repeated sequence is C, or next most repeated byte is C, and it gets the next shortest code symbol, and so on and so forth until you get down to O, which is only seen once, and it's going to get the longest code symbol. And what that does is it takes what would typically a full ASCII character, and it reduces that down to these binary pieces of data. And then that causes further compaction because essentially you're taking byte-wise encodings and bringing them down to bitwise encoding that's tailored toward the data that you've seen. So you're tailoring it toward these high frequency symbols. So those two techniques are the basis of a lot of the lossless compression techniques. Certain algorithms or formats will do both stages. Some will only do one, and it's really at that point it's a question of how much compression ratio do you want to get, as opposed to how much do you want it to cost in doing that. And I'll get into that kind of analysis in a minute. But again, this entropy encoding is really trying to say, take your these byte-wise symbols and compact them down to these binary formats that allow you to get this type of compression. So we go on to some of the algorithms. We've got this swathe of algorithms in the lossless compression space. There are some that are highly focused, as in there are some that are very popular and get used in a lot of different applications. But essentially, there is a large space of algorithms, and they tend to balance based off of speed and compression ratio. So I took some of the most popular examples of algorithms. So if we go down through the list, we've got Z-standard, Brotli, Deflate, and Express. I've bucketed those into this concept of a balanced set of algorithms. They all provide a number of different levels, ranging from very low compression or low compaction rates, and these higher ratios where they're not compacting the data, to much higher compression ratios that consume more cycles. So essentially you have this swing of data going from low level, where you get good ratio but not the best, and the cycle counts are quite low, so it's fast, to these very high compression ratio numbers that give you good compression, but they cost a lot of cycles. And I have data on the next slide to actually show that. Then we get into this other category of algorithms, which is really these very fast algorithms. They lose, in the context of compression, they lose a lot on compression ratio, but they're really tailored, even from a format perspective, they're really tailored toward being both fast on compression and exceptionally fast on decompression, where the format is actually tailored toward the ability to decompress it. So if you look at where some of these are exposed, they get exposed into a lot of different software stacks. So if you look at the Linux kernel crypto framework, it's got access to a number of these more predominant algorithms. ZFS, BTRFS, SquashFS, all of these support different compaction algorithms, again, from the list that I've described. Databases, standard file zip utilities, and HTTP encoding, as John had mentioned. A lot of the web servers will have integrated in both Deflate, which is from the zlib library, or they'll integrate in things like Brotli, which is tailored toward a HTTP type encoding stream. And they'll do HTTP encoding, which is a flag inside the HTTP standard to allow you to pick different compression algorithms. In the context of HTTP, one thing to note, you have HTTPS, which adds encryption through TLS and or QUIC. The one thing to note is that when you're doing encryption and compression together, you want to compress before you encrypt. The act of encryption is randomization of data. That's its primary purpose, is to randomize the data. As we saw from the description of the algorithm, if you randomize and heavily randomize the data, you don't have data locality. You don't have this idea of being able to find matches easily. So what you'll find is that if you encrypt and then compress, the compression activity will be it won't be very profitable. You won't get good compaction. and you'll spend a lot of cycles working on it. So you always want to compress first and then encrypt afterward. If you look at some of the techniques that are employed, we've got LZ77, 78 that I had mentioned. We've got Huffman encoding, which I gave a very simplistic example, but not a balanced Huffman tree. Finite state entropy. Burst-Wheeler, this is another transform, which is basically takes the data and tries to bring similar symbols together so that you can run another technique like an RLE, which is a run length encoder, that basically says if I have repeated symbols, how can I represent it in a much smaller way? So there's a lot of techniques. Pre-built dictionaries is one that's getting a lot of focus now. This is the concept of, well, what if I had a piece of data that I virtually appended to the data stream that I'm trying to compress, and I can use that as symbols to look at. That has multiple advantages in that you can start compressing from the very start. As we saw in the previous example, you don't have history, so you can't find matches, whereas in this case you can. The other advantage is that you can also not have to transmit some of that history, and you can share that across multiple data sets. So if you're doing something like an XML or a markup language, there's going to be a lot of similarity between files, and you can build these effective dictionaries to manage that. And then we kind of see down this side box here. This is just some other algorithms that that are in the compression space. This is by no means an exhaustive list, just some other popular ones. But as you can see, there's a lot of different techniques. There's a lot of different formats, and a lot of different ways of compressing data. And it all leverages around this idea of how much ratio are you going to get to the performance that you need to hit. So now we get into the data, right? So if we look at some of the performance numbers, this is taken from a site called LZBench. It's a GitHub project. Really good site in that they take a number of different compression algorithms and they run it against the standard corpus, which is a kind of a set of data files that is generally recognized as a good example of what you will see in the compression space. And then in this case, they run it against the Celestia corpus. And essentially they plot out what's the ratio that you achieve with different levels of these algorithms compared to the cost. So how many cycles is it going to take to run these algorithms? So what you see on the left-hand set of the graph is really the compression side of the equation. So you have ratio up the left-hand side and cycles per byte along the x-axis. And now what we see is that and just to mention, lower ratio is better because that's the percentage of the original data set. What you see is you have a lot of algorithms that can get these good ratios around like 30%, even up to 40%, and then they're at a sub 500 cycles per byte. Some of these are much lower. Some of these are like in the tens of cycles per byte. And again, you start to see this breakout. Like if you took LZ4 fast 3, it's a very fast compression algorithm, but it only gets 50% ratio. So what you see is that this tends to tailor itself toward applications that need very fast performance, but may not need the best of compression ratios. On the other end of the spectrum, you've got the Z standard level 22 or the LZMA 9. These are very good compaction algorithms. They do a lot of work in their techniques to try and find matches and to compact the bit symbols much better, but it takes a lot of cycles. You're up in the thousands of cycles per byte, and there are very few applications in real time that can tolerate that cost. So really, these balanced algorithms are trying to provide a way of giving you options and giving you options on how you actually pick the algorithm that best suits your application. What you'll see on the right side of the graph is the decompression performance versus ratio curves or plots. And the takeaway here is that you see a lot of algorithms are clustered in the decompression space. So they tend to cluster around having a reasonably good decompression speed. So if you imagine from a storage perspective, you're typically going to be doing more reads than writes, and it's typically not something that you can delay. People are going to do reads and they're going to want their data back quite quickly. Whereas on a write, there are a number of techniques to delay the write and the commit to actual storage before the user doesn't basically get blocked by those commits. So you can do advanced techniques in the background on the compression side. On the decompression side, that's much trickier. So you tend to want a decompression algorithm that's very fast to respond, very fast, therefore, to decompress. And what you see on the decompression side is this tight clustering. And what really affects the decompression speed more so is the format rather than the original techniques that were done in compression. Now, some of the original techniques that are done in compression, if you're doing a two-phase process, have impacts. But really, if you can tailor your format to an architecture that allows you to decompress fast, it gives you greater gains. And then just one thing to note on the compression side, you see that like the Z standard, say level 19 or 18, as opposed to like the Z-Lib level 9, there's a swing of maybe what 4 or 5% ratio, if even, but it costs a lot in the context of cycles per byte. So these higher compression ratios, while there is gain, it costs a lot to get a few percent. And in some cases, that makes a huge difference in some cases if you're talking about petabytes of data. But if you're talking about very small requests, it may not be profitable to do that. And then my final portion of this is this real-time versus post-processing. And I kind of alluded to it in the previous slide where we're looking at the performance characteristics. But really, the decision is up to the application. And those decisions tend to get made in the context of, well, how responsive do I need to be? What's the throughput that I need? And how much? Everybody wants to get better ratio. Everybody wants to get further compaction because it just adds benefits. But you can't go so far that your application can't tolerate it, or you cause a reduced quality of service. So for example, if decompression of HTTP frames slowed down the response to a customer so dramatically that they can see it, that's not profitable anymore. You'll start to lose users on your website. So there's a fine balance on how you do these techniques, but it really comes down to one of cost compared to how much ratio I can get, because you always want this better ratio. So some real-time applications would be things like file system reads. So the decompression space, that tends to be a space where you have to have this real-time characteristic. HTTP encode and decode. These can be large blocks, but again, if you're going to impact the user's experience by spending a lot of time decompressing and or compressing, you're going to lose users. So you would tailor toward actually sending the data raw rather than compressing in some of those cases. So that's a real-time characteristic. Post-processing and offline is a great example of a non-real-time or use an algorithm that gives me the best ratio. So you will see, like in log files, LZMA and Z standard are used quite heavily, and that's because they give really good compression ratios, but they cost. And in log files, there isn't usually a real-time need to get it submitted to your storage device, so you can take that time to compact them. You may do things like write them and then take them back out and compact them tighter over time when your system has bandwidth to do that, or CPU cycles to do that. And then this concept of cold storage tiers or tiering in general, each tier will have a level of warmness, say, or how active they are. And the less active ones, you can take the time to do higher levels of compression and push the data out to storage so you get best utilization of your storage space. So with that, I will hand it back to Ilker.
Thank you, Brian. I learned a lot from your session as well. I hope the audience did too. So just to wrap it up, so what we learned today is the compression saves space, bandwidth, improves total cost of ownership, whether it's in the data center or in storage. And some types of data can be compressed more than others. So identifying those is really important. And the key thing is data can be compressed while transmitted, stored, and backed up. And there are several proprietary and open source compression algorithms, but the important part is choosing the right compression algorithm for the workload. That's going to be the key for performance and cost. So, gentlemen, we have several questions from the audience. I would like to use the rest of our time to address some of these questions. So given our time, you already addressed the Brian encryption and data compression. I'm not going to dig into that one again. But one of the questions the audience asked, when multiple unrelated entities are likely to compress the data, how do they understand the data is already compressed or we skip this compression? Do you, either of you want to take this?
Yeah, so I mean, typically all of these, and it's something I didn't mention, is typically these compression algorithms are broken into two distinct portions. Usually they're broken into a compression block and then a format. So what's kind of there is like a format would be, say, zlib or gzip, or zstandard is both it can be both a compression block and a format. But the format really encloses that in a header that tells you what the data is, and like checksums around the data to provide data integrity. So if you have data that's stored, you would typically have these headers around them to tell you that the data has already been compressed. If it's just raw storage and you don't know what the data is previously, there isn't really good ways of telling that it hasn't been compressed. There are some techniques where you can pre-process the data to see how much repetition there is in the data, and you could use that type of technique. But again, that costs. So is it more profitable to just start the compression work, or is it better to identify if there's repetition? That really depends on your application.
Okay, thank you. Thanks, Brian. And yet another question on storage efficiency of the data reduction techniques. On certain database and server workloads, and such as Oracle ASM, which doesn't perform very well under any form of storage efficiency method. In such scenario, what would be the recommendation to ensure storage is utilized correctly? Does any of you want to take this one? I think the questions are on the Oracle ASM. Yeah.
Right. I think the question is not really how do we compress Oracle ASM. I think the question is if you have some data where compression is not practical or compression is going to hurt the performance, what else could we do for storage efficiency? And I first say there was actually a recent SNIA-NSF webcast that covered other storage efficiency technologies at a high level, and it would be probably good to go, if you haven't seen that one, it'd be good to go watch that webcast. But some examples are you could definitely use things like thin provisioning, or possibly hole punching, or snapshots and clones to help reduce for storage efficiency, even if you cannot use compression. Now, snapshots and clones usually only provide savings if you had to make backup copies, or copies for other people to work on. Then they provide space savings. They don't provide any savings if you didn't want any copies or didn't need any development versions of that database. If I recall, I think deduplication is not normally very efficient on databases, but again, some database engines actually can do compression at the application level, which would probably be a lot more efficient than compressing at the storage level if the database didn't like that, or if that hurts the performance. Brian, do you want to add anything on to that?
No, I think that's really good. I just highlight the one particular point you made there is that compressing where you understand the data is always more profitable. You can pick the algorithms that understand your particular data set and apply them the best. Compressing at lower levels, essentially you don't know what data you're compressing, so you can't really you have to pick general purpose compressors, and you can't make a lot of decision there. So if you can compress at an application level, it typically gives you better ratio, because you can do things like, say, dictionary encoding that allow you to get higher compression ratios even for smaller blocks.
Very good. Thanks, Brian and John. There's another question. This is to do with the lossy compression. How do we guarantee the important information not losing during the lossy compression?
So usually the compression techniques that are used for photos or video and audio usually are designed, in fact, they're almost always designed to try to lose the least important bits of that data. So for example, with video, if they see that a portion of the video is unchanging, so let's say only there's no motion going on, then they'll do more aggressive compression because they can just show the same frame over and over while there's no motion. And then if the motion starts up in the video, but it's only in, say, the upper right corner, there are maybe algorithms that can try to do aggressive compression on the bits everywhere else in the frame, each frame except the upper right corner, because if the only changes on the upper right corner, then that's where you have to preserve the data. So I think generally you just have to trust that you're using the algorithm that's the best combination of efficiency and not losing any of the important bits. They're losing just the less important bits of data. Brian, you probably have some better insight into
yeah,
that.
well,
expand on that.
Yeah, I'm by no means a lossy compression expert. It's very much a field in and of itself. But you'll see that a lot of the lossy compression algorithms, whereas we looked at compression ratio and throughput, a lot of them actually have grading scores onto how much fidelity they had with respect to the original image. Let's take the case of image compression. So a lot of the algorithms are graded based off of how much loss you can actually tolerate with respect to the original image. And then you choose those accordingly. 100% fidelity, if you wanted 100% fidelity, you really need to go to the lossless, but in the space of lossy, they do have these kind of grading schemes of how good the algorithm is.
Very good. So let's take a couple more questions from the audience. And this is to do with the more in terms of resources. Is there a resource for different algorithms versus CPU requirements and the compression ratios?
That's a Brian question.
Yeah, so can you repeat that?
Yeah, is there a resource for different algorithms versus CPU requirements versus compression ratios? I think the question is, is there such a CPU requirement to handle these algorithms or not?
Or maybe they're looking for a resource guide or like something a reference that tells you which algorithm to use.
Yeah.
Okay. So that's the algorithm to use is really an application choice. And what you'll see is that the choice of algorithm, you tend to go through the popular ones that I mentioned there and see which ones actually suit your purpose and integrate that into your application. What we're seeing more of today, because there are some more specialized compression algorithms, a lot of frameworks are adding a plug-in interface so that you can actually choose different algorithms depending on what you want to do and then tailor it accordingly. From a CPU perspective, what you start to see is, as we saw with the LZ77, a lot of the cost is in searching. So it has impacts based on both memory traversal, so caching impacts, along with just CPU calculations and comparison logic. In the decompression space, it's a lot of data movement, so it has a memory bandwidth impact and again, a caching impact. So the trade-offs are really based off of what system you're trying to land the compression algorithm on and how capable it is. Does it have access to a lot of low latency, very performant cache? And then the other aspects are how much you can tailor it toward your application and your data sets.
Thanks, Brian. Maybe this is another question for you. Is can you please characterize the performance difference between, let's say, LZ4 and deflate, if there's any latency differences, microseconds or nanoseconds?
So I won't get into specific numbers. If you want specific numbers, I would highly recommend going to the LZ Bench website. They've actually got the throughput numbers there. But from a latency perspective, LZ4 is very nicely tailored toward a standard byte-wise instruction set. The decompression speeds are very fast. On the compression speeds, it's also exceptionally fast. Deflate is a good format, but it has been around for since the kind of 70s and 80s. Where it got popularized. So it's widely used, and there are a lot of optimizations on it, but the format itself was never tailored specifically for speed. LZ4 does not get the same kind of level of compression ratios, but it has very fast performance.
Thanks. I think we'll take one more question, and then we'll move on. And I like this question. Before compressing the data, is there such a method to check if the data is good to be compressed?
Yeah, so there are some techniques to just do a precursory scan of the data to see if there's repetition. Essentially what you're doing is you're looking for data locality. There's also some techniques to pre-format the data to get better compression. So Burris-Wheeler is a good example, where you start to bring multiple symbols together that are the same, and you bring them to closer localities so that you can find the matches with more advanced algorithms like LZ4, or even algorithms like run length encoding, which is quite a straightforward technique. So there are some algorithms out there that, or there are some applications out there that do this precursory scan of the data. And I think there is actually one as part of the Z-Standard project that they use for building their dictionaries as an actual application. But again, there's these techniques out there that you're just essentially trying to very quickly scan the data and see if you get repetition and see if it's profitable for compression.
Excellent. Well, gentlemen, John, Brian, thank you very much for the webcast today. If I may give the audience, we have upcoming webcasts in series. We have two product ask on the data reduction, and also we have a data duplication for storage systems in October. Please follow us in the SNIA website. And also in BrightTalk for upcoming webcasts. Thank you for all listening us and join us all around the world. Have a great day. Thanks.
Thank you very much.
Thanks.
Thank you, everyone.